All right, this is AP Physics 1, Forces Part 3, really is what I would call it. But it is about our statics, okay, and how we're going to do problems with multiple forces and systems, okay? So the first thing in your note packet is just talking about a problem solving strategy when we do these types of problems, okay? So when we do these types of problems, the first thing you're going to want to do is draw a sketch of what's going on. You're going to want to draw, lines. You're going to want to draw a box for a picture or for a crate or something. And then you're going to label everything that you've got. If you know mass, you're going to put mass on it. If you know any tensions, you're going to put tensions on it. So you're going to do all those kind of things. Then you're going to draw a free body diagram. Always in that free body diagram, you should be including your weight, which we know how to solve for, and then any other forces that exist, you're going to put those on there. If you have any angled forces, which you typically will on these types of problems that we're going to be doing, you're going to have to find the components of all those forces. You're going to remember to label them as either positive or negative, depending on what direction they're going to, like X is to the right or positive, and X is to the left or negative, and Y is up or positive, and Y is down or negative, and then remembering how to solve for those components using sine and cosine. Then we're going to apply the first condition of equilibrium. A lot of y'all are going to go, we don't even know the first condition of equilibrium. But yes, you do. These are going to be statics questions, is what we call them. And statics questions are things that are typically like hanging. And if things are hanging, then they're not moving up or down, and they're not moving to the left or right, like a picture on the wall. So the first condition of equilibrium is that the summation of all the forces in the x-plane has to be 0. And the summation of all the forces in the y-plane also has to be 0. So pretty much your net force overall has to be 0. That's the first condition of equilibrium, and that's going to be real important that we follow that as we do these types of problems. Then you're going to solve for any unknown forces or angles by setting up information about those net forces in the x and the y plane. All right, so let's try it. We have an example 10 in your packet, and it was originally example 10 because this used to be included with your previous forces packet, and I broke it into 2 units, separate units, so that's kind of why it's numbered strange. So I have a 50 Newton sign that hangs by a single wire as shown in the picture, and you guys have it as eat at its, okay? And I want you to find the tension in the wire. My picture says bears instead of eat at its, but it's the same thing. So we've got the sketch because I've already given you the picture. Then the next thing that I told you to do was to draw the free body diagram. All right, so we know that there's a weight force, and we know that there are 2 tension forces in the wire. So we have our T1, our T2, and our weight force. Now, I label my weight force most of the time F of G. I borrowed this particular setup from a friend, and she likes to label it F of W. So all of these will be F of W for the F of G. So I did tell y'all that sometimes it'll be a little bit different, but okay. So there's my free body diagram. All right. I did know, and I'm going to go ahead and make this statement now because it was on here. I did know that this was 100 degrees. Okay, so if I bisect that, that means that's 50 on each side. So I could say that the angles right here are worth 40 degrees on both sides. That's what I had written before showed this. Okay, because after you draw your free body diagram, I told you to go ahead and do your components. So your components would be your T1X and your T2X, and then you would also have your T1Y and your T2Y. If you're doing this at home, you have your note packets, you're listening to it, you need to be filling in your note packets as we're going along. All right, so if we have the sides of a triangle and we know the angle, we can find those sides by using sine and cosine. We are going to go back to our trig and we can figure out that information. All right, because we could say that T1x is going to be our cosine theta times T1. And then this is going to be sine of theta T1. And this one's going to be cosine theta T2, and this would be sine of theta T2. So those would be how we would solve for those t of x's and t of y's. All right, so I'm going to find the sums of the x and the y components. So I'm going to talk about my net forces. So I know in my x-plane that everything has to be 0 because my sign's not moving back and forth on the wall. Okay, so in the x-plane I have a t1x and a t2x, but they're going in opposite directions. So I'm going to go ahead and subtract those, but they equal 0 because those are the only forces in the x-plane. Now, I do know that I can expand those out, and it can be T1 cosine theta and T2 cosine theta. So if that's the case, I can plug those cosines in and T1 and T2. I can then realize that my angle is 40 degrees, so I could substitute that in and have T1 cosine 40 minus T2 cosine 40. All right. Then I can rearrange the equation so that the T2 cosine 40 is on the other side. Add it to both sides. And then if you notice that cosine 40 is on both sides, and if it's an expression's on both sides of an equation, it is able to be canceled out. So then we would just have T1 is equal to T2. Okay? So that's a pretty easy expression just to set up as far as just saying what can we say about those two tensions in this scenario. Okay? So that was for our x-plane. Now we need to find the summation of our y-plane. So we know that the summation of our y-plane is also 0 because the sign is not moving up and down on the wall. All right. So we have T1y plus T2y minus our F of W, or our weight force. And all that has to equal 0. And we have the subtraction of the weight force because the weight force is going in the opposite direction of the Ty values. All right. So we can then substitute, we know how to solve for those y's as T1 sine theta plus T2 sine theta minus our F of W. We can then substitute in some known values. We know the angle to be 40 degrees, and we also know the weight force to be 50 newtons because we were told in the actual question that it was 50 newtons. We also know one more thing. We know that T1 is equal to T2, and right now I have two unknown variables. I can't solve for two unknowns at one time. So I have to make sure that I'm only trying to solve for one. So what I can do is I can substitute in T1 for T2 because they're the same value. So now if I look at it, I only have one variable to solve for. So when I simplify this expression, I now am going to have 2T1 sine 40 minus 50 newtons all equal to 0. I can solve for that because that's just one variable. So then if I rearrange it to solve for t, that's 50 newtons divided by 2 divided by sine theta, or sine 40. Okay? So once I do that math and I solve in my calculator, I can find out that T1, which is equal to T2, are both 38.89 newtons. So I will tell you when the angles are equal like this, the T1 and the T2 will always be equal to each other if the angles are the same. If the angles are not the same, that is not true. So it's important that you understand how to create this process because the angles are not always going to be the same. I am going to tell you that. But for this example, they were, and so we were able to set up the expressions the way we were. Okay, let's move on. In example 11, I have a 50-kilogram crate which is hanging on a 4-meter long rope. That rope sags 5 centimeters. What is the tension in the rope? Again, sketch the picture, which I have the picture in your notes for you. All right. And then the second part of our problem-solving strategy is to go ahead and draw a free body diagram, which you can draw it separately or on the picture. I'm not picky, whatever works for you. Then we are supposed to fill in our components. So we have T1x and T2x and T1y and T2y. And then we're supposed to find the sum of our x and y components, or the sum of our x and y's. Okay, so we know that the summation of our f of x's is 0. So we can say T1x minus T2x equals 0, which if we go through the same process that we did last time, we would be able to say that T1x is T1 times the cosine of theta, and T2 is T2 T2x is T2 cosine theta. So we would be able to say that T1 and T2 are equal because, again, this was hung in the middle. These angles are going to be the same. All right. Then for our y, we can say that T1y plus T2y minus our weight force is equal to 0. Now we can substitute in those components as T1 sine theta plus T2 sine theta minus f of w. Okay, well, first of all, we don't know the f of w. We also don't know the angle. But we can find the f of w. F of w, if you remember, is just mass times gravity. So since that is just the weight force, it's 50 times 9.8 meters per second squared, which would make our f of w 90 degree, or 490 newtons. All right, so then we could simplify also because we know T1 is equal to T2. We could say 2T1 sine theta minus 490 newtons. Okay, but how do I find that angle? Let's think about that for a minute. All right, so I know some additional information in the problem. I know some distances. So if I really think about it, I know the 4-meter long rope. Well, I hung the crate in the middle. So I know that that horizontal distance is going to be 2 meters. I also know that the rope sagged 5 centimeters. So that would mean my vertical distance is going to be 5 centimeters. Oh, hold on. Centimeters, can't use that. I have to change it to meters. So there's 100 centimeters in a meter. So I'd have to divide by 100, which would tell me that there's 0.05 meters. So if I know two distances of, or two sides of a triangle, I should be able to find an angle by doing tangent. Okay, so you should be able to do the inverse tangent of 0.05 divided by 2. So you should be able to come up with the angle value as 1.43 degrees. And it's a little bitty tiny angle, but when you really think about it, that's not a very much of a sag. So it's not going to create this like giant angle anyway on the rope. Okay, so now I do know my angle value, so I could plug that in over here. All right, and then I could solve for T1. So when I do that, I could do my 490 divided by 2 divided by sine of 1.43 degrees. When I do that, I get an answer of T1 is equal to T2, which is equal to 9,803.06 newtons. Okay? So make sure you go over these as far as with the same angle and that you understand the summations of the x's and the summations of the y forces and those kind of things. If you have any questions, bring those to class. Okay? Now, we are also going to do apparent weight so that I can have you guys up to speed tomorrow. And so apparent weight was one of your questions actually in your homework problems for the last unit. And so this is going to kind of clarify some of that. Some of y'all were able to figure it out without this, but I did want to kind of go over and explain it some more. Apparent weight is a force that acts in opposition to gravitational force. And it's in order to prevent a body from going into free fall. Okay, so it is always in opposition of gravitational force. When you stand on the floor pushes up on your feet with a force equal to your apparent weight, which would roughly mean that your normal force is equal to your apparent weight. Okay, so as you sit in a chair, you feel a contact force, which is a normal force, and that's a balancing the non-contact force of gravitational force, which is a field force. All right, but if a person is in free fall, they don't actually experience any of that apparent weight or contact force anymore, so they do feel weightless. I'm not going to move my little recording screen because when I move it around it gets lost and then I lose my recording, but that's what that says behind that, is that thus they would feel weightless. Okay, so let's talk about that a little bit. When you are in an elevator, your actual weight never changes. Mass times gravity is what it is. But you will feel lighter or heavier during the ride because of your, quote, apparent weight. That's going to increase when you accelerate up because you're having to overcome gravity and accelerate up. So you're actually going to feel heavier when you go up. And then when you go down, that acceleration is actually helping gravity out, so it subtracts from it. So it actually makes you feel lighter when you're going down. And then if you're not accelerating at all, then your weight force is your weight force. It's equal to exactly, your apparent weight's equal to your actual weight. So those are some kind of things to think about. So let's talk about example 12. We've got an 85 kilogram person who's standing on a bathroom scale in an elevator. Yes, I know it's weird, but it works, okay? And I would actually like to try this. I think it would be really fun, like in a really high-rise building that had really fast elevators, but I don't know. So let's figure out first what is just the person's regular weight. So what we would do is we would take just their gravitational weight is going to be mass times gravity, which equals 85 kilograms times 9.8 meters per second squared. Okay, so when I do that, I do 85 times my 9.8, which is going to give me 833 newtons. That's their actual weight, okay? Now, if an elevator is accelerating upwards, then they're actually going to have to be going at least as fast as gravity to be going upwards. So they have to overcome 9.8 meters per second squared acceleration, plus they have to go an additional 2. So if we wanted to find their apparent weight, remember their apparent weight is actually going to be equal to their normal force, all right, that they're going to feel, because it's always in opposition of the downward force. Okay, so if that's the case, then we can say that the net force is equal to the normal force minus the F of g. Okay, if that's the case, net force is found by doing mass times acceleration. Normal force is what we're trying to find, and then weight force is mass times gravity. Okay, so if I know my mass is 85 kilograms, actually, let me rearrange the equation first, and then I'll do that. So then I have mass times acceleration plus mass times gravity equals my normal force. So if I factor out my mass, then it's just acceleration plus gravity, which equals my F of n, which also equals my apparent weight. All right. So I know my mass is 85 kilograms. I know the acceleration is 2 meters per second squared, and I know gravity is 9.8 meters per second squared. That is then going to give me 1,003 newtons, I believe. Let me double check that. 85 times 11.8. Yes, gives me 1,003 newtons. So they would actually feel heavier. This is also what happened on your homework problem, because he was accelerating upwards in the rocket, and that upwards acceleration had to overcome gravity as well as accelerate him up. So you had to add the acceleration value that you found to gravity and then multiply it by the mass to figure out the apparent weight. So they would feel heavier. Now, when the elevator is moving at a constant velocity, that means we're not accelerating. So the apparent weight here, or my normal force, would be the same as my weight force, which would be 833 newtons. Okay. And then if I was talking about the elevator was slowing at the top, now the acceleration's going actually down. And so when I really think about it, my net force is equal to, now if this one's the case, since it's going down, then my F of g is actually winning, and it's minus my F of n, because F of n is going up, and my acceleration is, remember, always going in the same direction as the force that's winning, all right? And so if I have my mass times acceleration equals my F of g minus my F of n, what actually happens is, as I rearrange things, okay, I would have my F of n would be equal to my F of g minus my mass times mass times acceleration. So I'd have my mass times gravity minus my mass times acceleration, and then if I factor out my gravity, or my mass minus acceleration equals that. So that would then tell me 85 kilograms times 9.8 meters per second squared minus the 2 meters per second squared, which would then be a value of 663 newtons. So we would feel lighter when we were slowing down. Okay? So hopefully those help. I would like for you, like I said, to get through this before we come in for class. If you have any questions about this information, we can discuss it then, and we'll get going with the rest of the notes next time. Thanks.